Black holes are among the most perplexing mysteries of the universe. For many years, both scientists and astronomers have been captivated by these mysterious celestial objects. However, one query remains persistent. Where does all the stuff that goes into a black hole go? Envision an environment where gravity reigns supreme, one so thick that light itself can elude its hold. This is the fascinating mystery surrounding black holes, celestial objects that cast doubt on our comprehension of the cosmos. But what does the event horizon actually mean? After stuff passes over this cosmological point of no return, what becomes of it? We must investigate the genesis, dynamics, and theoretical ramifications of black holes in order to provide answers to these concerns. These objects are zones of space-time wherein the force of gravity is extremely strong, not just voids in space. The true mystery starts at this limit, also referred to as the event horizon. How black holes form. So how can black holes form? Let us begin at the outset. In essence, stars, those dazzling lights in the night sky, are enormous nuclear reactors. They burn hydrogen over the majority of their existence, a process called nuclear fusion. The star shines because of the tremendous quantities of energy released during the conversion of hydrogen into helium. However, stars possess a life just like anything else. A big star runs out of nuclear fuel as it gets closer to the end of its existence. In the absence of the external force produced by fusion to offset gravity, the star is unable to sustain itself against its own mass. This is the start of something truly catastrophic. One of the most catastrophic occurrences in the cosmos, a supernova explosion, results from the star's core collapsing due to gravity. The star's outer layers are shot into space, but if the core is large enough, it will continue to collapse and eventually form a black hole. There's a place where the gravitational pull is so great that not even light can escape because of this collapse, which is so strong that it warps space-time itself. A black hole forms in this manner. However, the tale is not over yet. The black hole is still interacting with its environment, taking in material from gas clouds, stars, and other objects that get too close. This material creates an accretion disk, a whirling whirlwind of gas, dust, and energy, as it falls toward the black hole. Extreme heat causes the matter in the accretion disk to spiral inward, frequently releasing X-rays, as well as other radiation with high energies. What occurs, though, when this stuff transcends the event horizon? We must investigate the idea of the event horizon itself in order to comprehend this. It is the point at which the speed of light and the escape velocity are equal. According to classical physics, anything that passes this boundary is lost to the outer cosmos forever. What comes next, though, is where the true enigma lies. Inside the event horizon. Come with me as we venture into the center of the black hole. The gravitational force becomes stronger as you go closer to the event horizon, distorting time and space. These impacts are more intense the closer you get. It appears as though time is slowing down because of the way light is stretched and curved. Einstein's general theory of relativity predicts this phenomena, which is the result of gravitational time dilation. The rules of conventional physics start to disintegrate as soon as you reach the event horizon. The phenomenon known as spaghettification occurs when items are compressed and stretched into long, thin shapes by the powerful gravitational forces. Imagine yourself being drawn toward the black hole's center while being stretched into the shape of a noodle. The singularity, a point with no mass and unlimited density, is located beyond the event horizon. It is believed that every particle of stuff that has ever entered a black hole has been compressed into an incredibly tiny point. But this is where the state of our knowledge of physics ends. The singularity denotes a point at which general relativity and other known rules of physics stop making sense. Space and time become so distorted near the singularity that our mathematical models are unable to capture what actually occurs. Does the matter somehow get ejected into another region of the universe, or maybe into a different universe entirely, or does it get compressed into an impossibly small point? Scientists are currently attempting to find answers to these questions. Theories and speculations. Scientist Stephen Hawking made a groundbreaking suggestion in the 1970s that expanded our knowledge of black holes. He proposed the possibility that black holes are not completely black. Alternatively, they might release what is now called Hawking radiation, a weak type of thermal radiation. The source of this radiation is the continual emergence and disappearance of virtual particle pairs due to quantum mechanical phenomena close to the event horizon. Every now and then, one of these particles may manage to elude the black hole's gravitational attraction and take Hawking radiation, which is a very small amount of the black hole's energy. This radiation may gradually deplete the black hole's energy over very long times, leading to its eventual evaporation and disappearance. However, this gives rise to an intriguing riddle called the information paradox. The information paradox. A disagreement among general relativity and quantum mechanics gives birth to the information paradox. Quantum mechanics states that a particle's state information, including its spin, position, and momentum, cannot be destroyed. This is the unitarity principle, which is a cornerstone of the theory. But what happens to the data about the matter that dropped into black holes if they can evaporate through Hawking radiation? A basic tenet of quantum mechanics would be broken if the data vanished in a black hole. If the data is retained in any way, how is it represented in the weak Hawking radiation? For decades, this contradiction has baffled scientists and given rise to a number of conflicting explanations. The holographic principle is among the most fascinating concepts. According to this hypothesis, a black hole's event horizon, the two-dimensional surface that denotes the hole's boundary, may include all of the information that exists within it. According to this perspective, this two-dimensional surface is sort of projected into the black hole's three-dimensional interior. The idea that our universe might be a holographic projection of data stored on a far-off border has significant ramifications for our comprehension of the nature of reality itself. A wormhole could allow the data to escape into a different universe, or it could be preserved in some other, as yet unknown manner. According to certain hypotheses, the singularity within a black hole might even represent the point at which space-time breaks apart, giving rise to a new universe. Should this prove to be accurate, each black hole within our universe may serve as the progenitor of a whole new universe, a notion that profoundly disturbs our comprehension of cosmology. Popular misconceptions. Black holes have captured the popular imagination like few other astronomical objects, yet this interest has also given rise to certain widespread myths. The idea that black holes are cosmic vacuum cleaners that are always expanding and engulfing everything in their path is among the most widely held misconceptions. In actuality, black holes, like any other enormous object in space, only attract objects that approach too closely by gravity. The orbits of Earth and the other planets would remain the same even if our Sun were abruptly replaced by a black hole of the same mass. The quick and catastrophic end of the solar system would not be the sole difference. The absence of sunlight would be. As a matter of fact, objects can dwell close to black holes without being instantly absorbed, and they can even maintain stable orbits. Another myth is that black holes are time machines or entry points to alternate realms that would enable time travel. Although science fiction frequently presents these concepts, there is currently little scientific data to justify them. Wormhole theories, which are still completely theoretical, are the source of the concept of employing black holes as gateways to other dimensions. If wormholes are real, they might be able to link far-off areas of space-time and create quick routes across the cosmos. Even if wormholes exist, utilizing them for travel presents considerable difficulties. They would probably be quite unstable, and trying to navigate them could be disastrous. Therefore, while black holes may spark creative ideas, the real world is significantly more complicated and less conducive to our fantastical visions. The ongoing mystery. Even with tremendous progress in human knowledge, black holes continue to be among the universe's most mysterious things. They pose serious problems regarding the nature of space-time, gravity, and the end of matter, challenging our knowledge of physics. Beyond being cosmic curiosity, black holes hold the answer to solving some of the universe's greatest riddles. The field of black hole research is dynamic and constantly changing. scientists can now examine these enigmatic objects in previously unheard-of detail thanks to the development of new telescopes and observational methods. For instance, in 2019, the Event Horizon Telescope gave us the first ever visible proof of the existence of black holes when it captured an image of their event horizon. In astronomy, this was a historic accomplishment that validated decades of theoretical effort. The discovery of gravitational waves has provided new insights into the study of black holes in addition to direct imaging. When two black holes collide or other enormous objects accelerate, they can generate ripples in space-time known as gravitational waves. It was previously difficult for scientists to analyze the properties of these waves in the manner that they can, since they convey information about the black holes that produce them. The nature of dark matter, the enigmatic material that accounts for around 27% of the mass energy content of the universe, may also be revealed by black holes. According to some hypotheses, black holes and dark matter may interact in ways that disclose the features of the latter. For example, dark matter particles may be attracted to black holes, which could have observable consequences that aid in the discovery of this elusive material. Furthermore, black holes are at the vanguard of the search for a theory of quantum gravity, which would combine the principles of quantum physics, which controls particle behavior at the tiniest scales, with general relativity, which characterizes gravity. Two prominent contenders for such a theory are string theory and loop quantum gravity, and black holes are crucial testbeds for these concepts. The goal of investigating black holes is to help physicists understand the basic properties of space-time. Conclusion: black holes stretch the boundaries of known physics to the absolute limit, hence representing the final frontier of our knowledge. We are continually reminded of the size and complexity of the world we live in as we investigate these celestial wonders. There is no end to the quest for knowledge, and black holes will surely enthrall and inspire future generations of scientists. Please like and subscribe to our channel if you liked this video. Your assistance enables us to provide more engrossing universe-related content. We appreciate your time and hope to see you in the upcoming intergalactic adventure.